Welcome to AI Paper Slop. Today we're looking at a paper titled, let me get this right, Proxy Exploration and Reusable Guidance, a modular LLM post-training paradigm via proxy-guided update signals.
Yeah, it's quite a mouthful.
It is. It's from the Shanghai AI Lab, Fudan University, and Zhejiang University, dated July 14th, 2026. And we're just going to jump right into this deep dive because the core insight here is huge for anyone doing ML engineering.
Absolutely. The TLDR is basically about how incredibly expensive post-training is right now.
Right, especially when you're using reinforcement learning, like PPO or the newer GRPO methods. It's just brutally expensive because policy exploration and policy alignment are totally glued together. You're forcing the massive model to actually do the trial and error itself.
Which is incredibly inefficient. So what this paper does is, well, it completely decouples them.
Exactly. They use a cheap, lightweight proxy model to do the hard work of exploring the environment and finding those high-reward behaviors. And then they extract a relative update signal from that tiny proxy and transfer it to a much larger primary model.
And they literally prove you can use a 1.7 billion parameter model to successfully guide the RL of an 8 billion parameter model.
Making post-training modular, cacheable, and just vastly cheaper for you to run.
Yeah, I mean, this completely transforms post-training. We are moving away from this monolithic, super expensive online process into a compress once, reuse many times paradigm.
Compress once, reuse many times. I love that.
Right. You can essentially mine the reward environment with a cheap little drone, extract this topographical map of how to improve, and then just upload that map to the mothership.
Okay, so to really grasp the engineering mechanics of this framework, which the authors call PUST, by the way, we need to look at the current bottlenecks. If you are an ML engineer running these pipelines, you probably already feel the pain of why existing methods are failing to scale efficiently.
Oh, for sure. Let's look at traditional serial reward optimization, which covers your standard PPO or GRPO.
The classic trial and error.
Exactly. The fundamental issue here is that the policy exploration, the actual falling off the bike, is happening directly on the target model.
Right, so if your goal is to optimize a 70 billion parameter model,
you are generating full responses, calculating rewards, and then back propagating through all 70 billion weights for every single step of exploration.
It's computationally brutal. You're doing on-policy rollouts at an enormous scale.
And beyond just the compute cost, if you try to do this sequentially across different domains, you hit a massive wall.
Catastrophic forgetting, right?
Exactly. Let's say you spend a week running GRPO on math data sets. The weights optimize for step-by-step logic. But then you move to coding data sets.
And suddenly the model starts forgetting how to do complex algebra.
Yeah, because the gradients from the coding tasks are literally overriding the math pathways. It's severe.
Which is why the field started shifting toward that alternative baseline, right? Parallel distribution alignment, or OPD on policy distillation.
Right. In OPD, you decouple the domains entirely. You train different expert teachers in parallel. So one for math, one for code, one for logical reasoning.
And then you just align a single student model to those optimized teachers via distribution matching. And the data in the paper shows OPD converges incredibly fast.
It does. I mean, for anyone who hasn't run this specific evaluation recently, the paper looks at the mean at 16 trajectories on the AMY 2024 and 2025 benchmarks.
Which just means they sample 16 different generation paths for a single prompt, right, to see how consistently the model finds the right answer.
Yep. And using that metric, OPD aligns the student in just about 20 steps.
Wow, 20 steps?
Yeah. Compare that to standard GRPO, which requires hundreds of steps of this long exploratory phase just to figure out what works before it even starts solidifying the good behavior.
I always look at this through a physical analogy. Using standard GRPO is like learning to ride a bike by just getting on and repeatedly falling off until your body figures out the balance.
Painful.
Very painful and highly expensive if the bike you are crashing is a massive 70 billion parameter model. OPD, on the other hand, is like simply watching a professional pro rider and mimicking their exact muscle movements. You don't have to fall.
You just copy the expert's distribution.
Right. And here is where I want to push back on the paper's main critique of OPD. The authors claim OPD is reward agnostic.
They do, yeah.
But if you actually look at the OPD pipeline, it uses URM, the update reward mask, and it uses FT, filtered trajectories. So it actively discards the bad generations and masks out tokens that don't contribute to a win. Doesn't that inherently mean OPD is aware of rewards?
Well, on a surface level, it definitely seems that way, but the paper argues that OPD is still fundamentally flawed in how it handles that reward signal.
How so?
Because even when you apply an update reward mask to hide the tokens that contradict the reward, OPD is only adjusting the model's probabilities based on trajectory level correctness.
Oh, I see. So it lacks strict token-level reward relevance.
Precisely, meaning it knows the final output was good, but it doesn't really understand which specific word actually made it good. It is, at its core, blindly matching an absolute distribution. If the expert teacher model did something weird and inefficient in step 3, but the overall trajectory was a success.
The student model just copies the weird inefficiency, too.
Exactly. True directional improvement, actually understanding which specific token increased the reward gradient, requires active exploration.
And with OPD, you are still delegating that wildly expensive active exploration to the massive teacher models anyway.
Right, the compute bottleneck hasn't disappeared, it's just been shifted to a different stage of the pipeline.
So we are still paying the computational tax of having massive models fall off the bike, just behind the scenes.
Exactly.
And that perfectly sets up the exact problem that Stage 1 and Stage 2 of the PUST framework try to solve: proxy exploration and update signal extraction.
This is where it gets really interesting.
Yeah, because if OPD just blindly mimics an absolute distribution, how does PUST capture the actual underlying learning without tying it to the specific quirks of a teacher model?
This brings us to the proxy model. In Stage 1, proxy exploration, instead of deploying your massive 8B primary model to do the trial and error, you deploy a lightweight proxy.
Like Qwen 3.1.7b or Qwen 3.4b?
Yeah, a tiny model that acts as a low-cost testbed. You let it run GRPO on datasets like DeepMath 103K for math or Eurostar code for coding.
It explores, it fails, it optimizes itself.
And it does so very cheaply because you are only doing forward and backward passes on a fraction of the parameters.
Okay, so you run this pipeline and you end up with an optimized 1.7b proxy. But wait, if we just distill that tiny model's knowledge into our 8b primary model, aren't we right back to the OPD problem?
How do you mean?
Well, we'd be forcing a highly capable 8B model to mimic the exact behavior of a 1.7B model, which would inevitably degrade the 8B model's performance, right? It's too small.
That is the exact trap standard distillation falls into, yes. And it's what Stage 2 update signal extraction completely avoids.
Okay, walk me through that.
Instead of doing standard distillation where the primary model copies the optimized proxy's absolute probabilities, PUST extracts a relative improvement signal.
The relative signal.
Right. They isolate the delta between the proxy's initial pre-trained state and its optimized post-RL state.
Oh, so they are essentially calculating the relative shift in the logits.
Exactly. The raw, unnormalized scores the model assigns to each possible next word. They are basically asking, in what specific direction did the proxy's logits shift to get better at this task?
This is a massive distinction. I mean, standard distillation is like copying a friend's exact GPS coordinates to find a restaurant. It's totally useless if you aren't starting from their house.
Right. If you just blindly copy their absolute coordinates from where you are, you'll end up driving into a lake.
Exactly. But PUST is like extracting just the turn-by-turn directions, like turn left here, go straight there, so you can apply those directional adjustments no matter where your starting point is.
That's a perfect way to look at it.
But as an engineer looking at this, I have to challenge the premise a bit. If the proxy is a tiny 1.7b model, its directions are fundamentally limited by its small vocabulary and weak reasoning, right?
You'd think so, yeah.
How can a model that can't even hold a complex 50-step mathematical proof in its context window give useful directions to an 8B model that can?
Well, to borrow your analogy, think of the 1.7b proxy not as a master navigator, but as an athletic coach.
Okay.
A gymnastics coach might not be able to physically execute a double backflip themselves. They lack the absolute capability.
Sure.
But they can still watch an athlete and say, tuck your knees tighter on the rotation. The coach understands the gradient of improvement without needing the absolute capacity to perform the feat.
Oh, that's fascinating. So during its RL exploration, the 1.7b proxy learns these universal microbehaviors.
Exactly.
What does a microbehavior actually look like in the context of an LLM, though?
It learns that outputting specific thought tags before generating an answer increases the reward. Or it learns that formatting its Python code in a specific modular way prevents syntax errors.
Or to double-check its arithmetic in step 3.
Right. By abstracting the learning into a relative directional update, the framework completely bypasses the capability bottleneck of the weaker proxy model. You aren't transferring the proxy's final answer, you are transferring the instinct of how to improve.
That makes perfect sense. Okay, so we have this extracted how to improve signal. But injecting that signal safely brings us to a major engineering hurdle in stage 3, signal transfer.
Yeah, this is the tricky part.
If you just take these turn-by-turn directions and start applying those gradients to the 8B model's weights, how do you stop it from overriding its own superior pre-trained knowledge? Like, if the EB model is already excellent at math, you don't want it wildly hallucinating just because a 1.7B model told it to aggressively shift its logits.
Exactly. If you inject the signal blindly across multiple steps, you risk severe over-updating.
Right.
Once the primary model shifts toward the proxy-suggested direction, continuing to push it in that exact same direction, token after token basically degrades the model's coherence.
So how do they fix that?
To solve this, the researchers use a mechanism called anchor-based update calibration.
Walk us through the actual pipeline setup for this, because the math here is elegant, but it requires a very specific architecture.
It does. During the transfer phase, you load your 8B primary model into memory, but you also make a copy of it and you freeze its weights entirely.
Okay, so that frozen copy is your anchor.
That's your anchor. As the primary 8B model updates its weights based on the proxy signal, you constantly run the same training prompts through both the updating model and the frozen anchor.
At the same time.
Yep. And for every single token generated, the system calculates the Kullback-Leibler divergence between them.
Basically, the log ratio difference between the updating model's probability distribution and the frozen anchor's distribution.
Exactly. So the system is constantly pinging the baseline to ask, how far have your current probabilities drifted from your original pre-trained self?
Ah, I see.
This divergence is used as a penalty term, denoted mathematically as delta theta. And to control how strictly this penalty is enforced, they introduce a calibration coefficient called lambda.
So what's the actual equation?
The final formula for the transferred utility is rho lambda equals delta phi minus lambda times delta theta.
Okay, just to clarify the variables for the listener really quick, delta phi is the directional update signal we extracted from the proxy model, right?
Correct. Delta phi is the push to improve.
And lambda times delta theta is the penalty for drifting too far from the anchor.
Exactly right.
I kind of look at lambda as the 8B model's ego, or its level of skepticism.
I like how.
Because a high lambda means the primary model is highly conservative.
Yeah.
It looks at the proxy's update signal and thinks, I'll take your advice on formatting, little guy, but I'm not drifting too far from my own mathematical expertise. I have a very high penalty for changing my mind.
Yeah.
But a low lambda means the primary model has almost zero ego. It recklessly follows whatever the proxy suggests, throwing its own baseline knowledge out the window.
And the sensitivity analysis in the paper maps perfectly to that concept. They swept different lambda values to see what physically happens to the model during transfer.
What did they find?
When they extracted the signal from a 4B proxy and transferred it to the 8B primary model, the optimal lambda was 1.08.
So just slightly above a 1-to-1 ratio between taking advice and remaining skeptical.
Yes. The 8B model could trust the 4B model's directions fairly well because the capability gap wasn't massive.
Makes sense.
But when they transferred the signal from the much weaker 1.7B proxy to the 8B primary model, the optimal lambda jumped to 1.57.
Oh, wow. So the skepticism had to scale with the capability gap.
It's mathematically necessary. The primary model needs to heavily penalize drifting away from its own anchor because the signal coming from the 1.7B model is inherently noisier.
What happens if you don't scale it? Like, what if you just force a low lambda anyway?
Well, if you look at their training graphs, when they force the lambda down to 0.5 for the 1.7B to 8B transfer, meaning they let the 8B model recklessly follow the tiny proxy performance, completely collapsed.
Really? Completely.
The gradient norm exploded, meaning the weight updates became massive and erratic, the training loss spiked, and the model's accuracy on downstream math tests literally dropped to zero.
It's like letting a toddler give you driving directions and you just blindly crank the steering wheel every time they point at a cow.
You're going to crash the car.
Exactly. But if you have a high lambda, you listen to the toddler say, turn left. You check the road yourself, and you make a minor safe adjustment to your lane positioning.
Exactly. The calibration holds the model steady.
Okay, so the calibration works in theory, but the real test for any ML team is whether this actually holds up against rigorous benchmarks. Let's look at the empirical results, specifically this weak to strong generalization they talk about.
The results on the Quinn3 family prove this isn't just theoretical at all. When they applied the PUST framework, transferring from the 4B proxy to the 8B primary, they saw massive gains across the board.
On which benchmarks?
On AIM 2024, AIM 2025, and the HMMT 25 benchmark.
Those are tough tests.
Very. And the most fascinating finding here touches on exactly how a weaker model can teach a stronger one. On AIM 2024, the 8B primary model achieved a significantly higher absolute score than the 4B proxy that actually generated the training signal.
So the student outperformed the teacher, basically using the teacher's own study notes.
Yeah.
Let's put some numbers to that for everyone listening.
So the 4B proxy model running standard GRPO scored a 58.8 on AME 2024.
Okay, 58.8.
But when the 8B model absorbed that 4B's update signal via PUST, it scored a 62.5.
Wow.
The signal's efficacy is actually amplified by the primary model's innate capacity. The 8B model takes the gradient of improvement and applies it using its much larger vocabulary and deeper pre-trained knowledge,
Reaching a state the proxy itself could never physically achieve.
Yeah.
That is wild. And they even demonstrated a transitive property to this update signal, didn't they?
Yeah, they successfully took an update signal from a 4B proxy and transferred it down to a 1.7B model.
Wait, down?
Yep. Then they took that newly updated 1.7B model, extracted its signal again, and transferred it up to the 8B model.
And it still worked.
It still yielded significant performance gains.
That's crazy.
It basically proves that these update signals are somewhat model agnostic. They behave like modular, transferable mathematical objects rather than brittle, model-specific weight updates.
I love that. But I have to play devil's advocate here, because if you dig into the data, there is a caveat the labs are definitely going to notice.
You mean the upper bound performance?
Yeah. The paper admits that proxy-explored signals, say transferring from 4B to 8B, are still slightly weaker than if you had just taken the 8B model and run the brutal, expensive GRPO exploration directly on it.
That's true. The direct 8B GRPO remains the upper bound for peak absolute performance.
So for labs that want the absolute best model on the market, aren't we inherently sacrificing state-of-the-art performance just to save a few compute bucks? Like, isn't PUST basically just a compromise?
I wouldn't call it a compromise. If we look at Figure 6 in the paper, the authors address this directly by contextualizing it within compute scaling laws.
Okay, walk me through that.
There is a slight drop in peak absolute performance if you strictly lock the number of training steps. But the data reveals something vital about resource allocation. There are diminishing returns to scaling the proxy model's size, but massive returns to scaling its exploration depth.
Meaning the number of steps it takes.
Exactly. If you take that tiny 1.7B model, and instead of training it for 500 GRPO steps, you extend its exploration to 800 steps, the quality of its transferred signal improves significantly.
Oh, I see.
It aggressively closes the performance gap with the larger models.
So you could literally substitute model size with longer, deeper exploration.
And because running 800 steps of GOPO on a 1.7B model is orders of magnitude cheaper than running 500 steps on an 8B model.
The unit economics fundamentally shift.
Completely. It becomes vastly more cost-effective to search deeply with a small model than shallowly with a massive one.
Because the small model can afford to take more steps, explore more dead ends, and refine its gradient of improvement, right?
Yielding a highly concentrated signal.
So you aren't really compromising on performance. You are just reallocating your compute budget from raw model size during the exploration phase over to exploration depth.
Exactly.
So bringing this all together, what does this ultimately mean for you, the listener, and your daily ML engineering workflows?
I think it signals the end of the monolithic post-training pipeline. PUST proves that post-training doesn't have to mean updating massive weights through online trial and error.
You can cache these update signals independently.
Right. You could deploy a fleet of small, specialized proxy models exploring different datasets simultaneously.
Like one mining math rewards, one mining coding structures, one exploring logical reasoning.
They extract these relative deltas and store them. Then your massive base model simply downloads the signals and calibrates itself in a controlled offline manner.
Which leads me to a final, slightly provocative thought pulled from the conclusion of the paper. Right now, in this initial research, that calibration coefficient we talked about, lambda, is just a static baseline number.
Yeah, set to 1.08 or 1.57 for the entire model during transfer.
But what if the future of open source AI is adaptive calibration? Imagine an architecture where the transfer intensity changes dynamically, token by token, based on local entropy.
Local entropy being a measure of how uncertain the primary model is about its next word choice.
Exactly. So if the 8B model is highly confident about a mathematical step, its entropy is low, right? So the system dynamically cranks lambda up.
Meaning the model ignores the proxy and relies on its own knowledge.
Right. But if the 8B model encounters a coding syntax it's really uncertain about, entropy spikes, lambda drops, and it heavily leans on the proxy's update signal for that specific token.
That would be incredibly efficient.
Imagine a near future where you don't have to download 70 gigabytes of whole model weights from Hugging Face just to get a slightly better coding capability.
Just pull a lightweight patch.
Exactly. A lightweight 50 megabyte update signal patch from GitHub, and you dynamically apply it to your custom-based models.
You're creating a truly modular mix-and-match AI ecosystem.
Instead of swapping out the whole bike every time you want to learn a new trick, you're just downloading the muscle memory of the pro writer and applying it to whatever bike you already own. Something to think about next time you are staring at a massive AWS bill for a PPO run.